Hello everyone, I am Prasanna from Georgia Institute of Technology. In this talk, I will be discussing an emerging memory solution to enable vertical scaling for NAND applications, specifically the retention behavior of ferroelectric NAND cells. 3D NAND has evolved over the last decade from 24 layers back in 2014 to over 300 layers in state-of-the-art products. This has been enabled by several innovations for logic scaling and physical scaling. Now, as we move towards the 1000-layer landmark, NAND is faced with multiple challenges. Scaling to 1000 layers at the same Z pitch will cause the NAND arrays to exceed the package dimensions. However, further shrinking the Z pitch is increasingly challenging due to lateral charge migration and associated reliability concerns. Over the last 2 years, ferroelectrics have emerged as a potential drop-in solution for the charge trap layer. On the left, we see the proposals for FE NAND from SK Hynix and Samsung. And on the right, we see our group's proposal back in IEEE 2023 for a ferroelectric NAND gate stack. Unlike charge trap flash, where the data is stored in the form of trapped electrons, the storage of data in the bound ferroelectric polarization provides a pathway for mitigating lateral charge migration while also enabling low write voltages. Before any discussion on ferroelectric NAND could begin, there was a critical challenge that needed to be addressed. Typically, the memory of the standard ferroelectric field effect transistor is limited by the coercive voltage of the ferroelectric gate stack. The coercive voltage is given as a product of the coercive field and the thickness of the ferroelectric layer. The vertical NAND design constrains the thickness of the ferroelectric layer at about 20 nanometers. And the coercive field of typical ferroelectrics like hafnium zirconium oxide is roughly around 1 megavolt per centimeter. This constrains the memory window of standard ferroelectric field effect transistors at about 3 volts. Over the last 2 years, several groups from industry and academia have proposed that the insertion of a dielectric layer into the ferroelectric gate stack could lead to enhanced memory windows. This has worked wonders, resulting in a multifold increase in the memory window over the baseline, enabling TLC and QLC operation. There are two common variants of a dielectric insert. The most common one is called the gate blocking layer, where the dielectric is inserted next to the gate. The other is called the tunnel dielectric layer, which our group introduced back in IEEE 2023, where the dielectric is inserted in the middle of the ferroelectric layer. So the big question is, how does the memory window increase? The current working theory is that the memory window enhancement comes from the trapped charges at the ferroelectric dielectric interface, be it the tunnel dielectric layer or the gate blocking layer. These charges sitting far from the channel IL interface boost the memory window by either negating the screening of the trapped charges or creating an internal dipole that aligns with the ferroelectric polarization. Okay, now let me present the retention problem. Retention is very crucial for any memory device, especially for a long-term storage device like a ferroelectric NAND or NAND in general. Here, we have a standard ferroelectric field effect transistor. It has a small memory window, but it is well known to have reasonable retention. So retention is being tracked here using a threshold voltage tracker over time. When we insert a gate blocking layer, that is a dielectric next to the gate, we see significant enhancement in memory window as described earlier. But results have shown that we also see significant retention loss in these devices. Now, when we move the dielectric to the middle of the ferroelectric gate stack, like in a tunnel dielectric layer device, we still retain the enhanced memory window, but this time along with significantly better retention characteristics. Okay, I showed you a bunch of cartoons. Why should you believe me? Let's look at some benchmarks. Here, on the x-axis, I am plotting the initial memory window. To start with, I am plotting the same on the y-axis as well. Everything is on ideal 1:1 line, which is great. We would like this to stay for time immemorial, but unfortunately, it does not happen. I would like to draw your attention to the blue dots here, which belong to the gate blocking layer devices. Now, after 10,000 seconds, we see that the memory window of these devices have dropped significantly, showing 25 to 50% memory window loss. Through this talk, we will explore why this occurs and how the tunnel dielectric layer devices enable robust retention while showing enhanced memory window. Before we start the study, we wanted to figure out the best tunnel dielectric layer and the gate blocking layer. So we sieved through multiple configurations and different materials, and we figured out that silicon dioxide acts as the best gate blocking layer and aluminum oxide acts as the best tunnel dielectric layer. So we went ahead and fabricated these devices using the gate stacks described earlier. Here we have a 14-4 gate blocking layer device, which has a 14 nanometer HZO layer with a 4 nanometer SiO2 as the gate blocking layer. On the right here, we have a 838 tunnel dielectric layer device, which has a 3 nanometer Al2O3 layer sandwiched between two 8 nanometer HZO layers. We perform extensive retention characterization on these devices. We use this pulse scheme here to perform the retention measurements. We initialize the device, we program or erase the device using a 10 microsecond pulse, and then we track the threshold voltage Vt of the devices using from the IDVG characteristics over time. We perform these measurements at three temperatures, 25, 75, and 125 degrees Celsius. Now I'll walk you through how the experimental results were obtained. Let's start with the 14-4 gate blocking layer gate stack measured at room temperature. There are two elements here. First, we show the IDVG characteristics, and then we use a tracker to track the threshold voltage as a function of time. We see the initial memory window here and the corresponding threshold voltages, and you see the enhanced memory window. For a 18 nanometer gate stack, we have a 6.55 volt memory window, which is an enhanced memory window. Now we let this evolve over time, and after 100 seconds, we visibly see a drop in the memory window. It has dropped about 15 to 16%. When we continue this experiment, after 10,000 seconds, we see about 29% memory window loss in these devices, as can also be visibly seen from the IDVG characteristics. Now, I have summarized the result for room temperature. Now we went ahead and did this experiment at 75 degrees Celsius and 125 degrees Celsius. Now, given that I walked you through the process for the 14-4 device, I'll go ahead and show you the results for the 838 device at room temperature, 75 and 125 degrees Celsius. Evidently, we can see that the memory window for this 14-4 device has degraded, while we see that the memory window for the 838 device here remains steady at 7.5 volts across the 10,000 seconds. There are two key retention mechanisms at play here. These are ferroelectric devices. Depolarization of the ferroelectric layer has been known to be the primary cause of retention loss in these devices. Second, we have seen that these devices have an enhanced memory window as a result of trap charges of the ferroelectric dielectric interfaces. Detrapping of these trap charges could also lead to retention loss. We will use these equations here at the bottom to extract information from the experimental results. So here we are presenting our time-dependent Arrhenius model to model the experimental results. Of course, this equation has a lot of parts, so I'd like to draw your attention to three components specifically. First is the temperature dependence of the initial memory window. Second is the temperature acceleration of retention loss, which is captured by the activation energy EA. The third is the time dependence of retention loss, which is captured by the time exponent N. Now let's go over each component separately. First is the initial memory window at each temperature. Here we have the initial memory window plotted on the y-axis in log scale, and 1 by kt, which is the indicator for time, plotted on the x-axis. For the tunnel dielectric layer gate stack 838, we see that the initial memory window is constant across time. Contrary, the initial memory window of the 14.4 gate stack degrades significantly as temperature is increased. This can be captured using a Arrhenius model as shown here, and the steep slope for the 14.4 gate stack shows the strong temperature dependence of the initial memory window. Now let's look at how the time-dependent retention loss is accelerated by temperature. We see that the memory window loss of the 14.4 gate stack is constant across all temperatures. Contrary, the memory window loss at room temperature for the tunnel dielectric layer gate stack is extremely low. And as temperature is increased, the retention loss increases, as indicated by the high activation energy. On the contrary, the gate blocking layer device has a near zero temperature activation. This drastic difference in activation energy between these two devices indicates that drastically different detrapping mechanisms are at play here. Based on this, we hypothesize that the retention loss in the gate blocking layer device is driven by direct tunneling through the thin gate blocking layer due to the high fields across the gate blocking layer. Contrary, trap-assisted tunneling, which is known to have strong temperature dependence, could be the dominant detrapping mechanism for charge loss through the thick heterogeneous layer in the case of the tunnel dielectric layer devices. The last component of our time-dependent Arrhenius model is the time exponent n, which captures the evolution of the memory window over time. Here on the right, we show the memory window loss against time plotted in a log-log fashion, and we see a linear behavior. The slope of these lines is the time exponent n. Here we summarize the time exponent n across different gate stacks. We see that the values are comparable, indicating that the time dynamics of retention loss is similar in all the cases. The power of these models is that they enable robust projection of memory window loss to longer times. Here we show the projected evolution of memory window up to 10 years for NAND applications. Alright, as we have seen so far, this is a complex physics problem. In order to understand the interplay between different retention loss mechanisms, we use Genestra, a defect-based device simulation platform from Applied Materials. Using Genestra, we simulate the evolution of the device at different stages. We start by assuming that the ferroelectric dielectric interface is overcompensated. That is, the trap charge density QIT prime is higher than PR, the remnant polarization. We call the initial state A at time T0, which is immediately after writing. We simulate the device at two more stages, B and C, at times T1 and T2, where T1 is an intermediate time and T2 is after a much longer time. We start by simulating the gate blocking layer device using Genestra. Okay, what does Genestra allow us to do? It allows us to look at the electric field across different layers. Further, it also allows us to look at the polarization map of the ferroelectric layer. Here, we also show a cartoon with the trap charges to allow us to understand the evolution of the trap charges at each stage. Before we start with the results, I'd like to emphasize that depolarization of the ferroelectric layer has been the bane for retention in these ferroelectric devices. Okay, let's look at the results now. Let's look at state A, which is immediately after programming. We see that the interface between the ferroelectric and the gate blocking layer is overcompensated. That is, QIT prime is greater than PR. In this state, the field across the ferroelectric layer is non-depolarizing. That is, the field across the ferroelectric layer is pointing in the same direction as the ferroelectric polarization, which is great, no depolarization. However, if you look on the other side of the interface, the field across the gate blocking layer is high, creating a trapezoidal barrier, which causes the trapped charges to detrap. Now let's look at an intermediate time B, when the QAT prime has reduced below PR. The field across the gate blocking layer has dropped, which is great because this contains the loss of memory window enhancing charges. However, now the field across the ferroelectric layer has turned depolarizing. Over extended periods of time, this depolarizing field leads to the depolarization of the ferroelectric layer, as can be seen from the back-switched polarization in the polarization phase map. So we spoke about a lot of things. So let me summarize all that here. Depolarization is the primary cause of memory window loss in ferroelectric field effect transistors. If the field is pointing in the same direction as the ferroelectric polarization, that is positive in this case, then the field is not depolarizing. If the field is negative, then the field is depolarizing. Now, as discussed earlier, in our case, we start with an overcompensated interface when the field across the ferroelectric is non-depolarizing. As QAT prime reduces below PR, this field turns depolarizing, resulting in depolarization of the ferroelectric layer. Now let's see what happens when the dielectric is moved to the middle of the ferroelectric gate stack, as in the case of a tunnel dielectric layer device. We again start with the initial state at time t0 and with overcompensated FED interfaces. We see that the field across the ferroelectric layers is non-depolarizing. But contrary to the gate blocking layer device, the thick heterogeneous layers prevent the detrapping of these memory window enhancing charges, thereby enabling them to stay there even after longer times. This in turn preserves the non-depolarizing field across the ferroelectric layers, leading to robust retention. Okay, now we looked at a lot of results and a lot of models. So now let's look at everything in perspective. So here we have a benchmark plot. On the y-axis, we have the memory window loss after 10,000 seconds, plotted against the initial memory window on the x-axis. We would love to have an extremely large memory window and extremely low retention loss, as indicated by the preferred corner in this plot. We have our initial set of standard ferroelectric devices, which we have been studying for about 10 years now. These standard ferroelectric devices have a low memory window but reasonable retention characteristics. Then we looked at gate blocking layer devices where a dielectric is inserted next to the gate. These devices have enhanced memory window, as you can see here, but they also suffer 20 to 50% retention loss. Third are the tunnel dielectric layer devices, which have the benefits of having an enhanced memory window, but at the same time also enable low retention loss operation. Therefore, we have shown that moving the dielectric to the middle of the ferroelectric gate stack energetically stabilizes the memory window, both through experiments and also through modeling efforts. So let me conclude my talk by saying this. Depolarization continues to be the bane for ferroelectric devices. When we insert a dielectric layer into these devices, we have memory window enhancing charges, and these memory window enhancing charges preserve or enable a non-depolarizing field across the ferroelectric layer, thereby solving the depolarization issue. Unfortunately, in the gate blocking layer devices, the memory window enhancing charges detrap through the gate blocking layer due to the high field across the gate blocking layer. Contrary, in the tunnel dielectric layer devices, where the dielectric is moved to the middle of the gate stack, these memory window enhancing charges do not detrap, thereby enabling robust retention without depolarization. That is it about retention. Alongside retention, disturb and endurance are the two other key reliability challenges in ferroelectric NAND devices. In our previous work published in IEEE EDL, we had characterized past disturb in these devices and also proposed a disturb mitigation scheme to reduce disturb down to 4%. Please do have a read if you have the time. With this, thank you for your attention and time. I would also like to thank all the sponsors and collaborators for their big support and contributions to this work. Thank you.